All right, so let's see, 10.5, part 2. All right, so what we're going to do here is like what we did when we talked about finding derivatives of polar, or derivatives in polar coordinates, is we're going to apply what we know about parametric equations to polar coordinates to come up with our methods for finding arc length and surfaces of revolution. Because we can think of polar coordinates as parametric equations. So for in parametric mode, or for parametric equations, where we have x equals some x of t and y equals some function of t as well. We had, for our arc length, we did a nice little argument, and we came up with arc length s equals the integral from a to b of the square root of dx dt squared plus dy dt squared. dt. All right, we're going to substitute x equals r cosine theta, and I'm going to say r of theta, cosine theta, and y equals r of theta sine theta. So our radius can vary with theta. We make this substitution. We do a little bit of algebra. It's not difficult algebra. It involves, I think, one nice trig identity, and we get that our arc length in polar coordinates, that our arc length is the integral from alpha to beta of the square root of r of theta squared plus r prime of theta squared d theta. And usually we drop the theta, the functional notation, and we just write that the way you'll usually see this is the integral from alpha to beta, the square root of r squared plus dr d theta squared d theta. And what we need to do, one thing that we need to be careful with, is we want to make sure that the curve is traced only once on the integral of integration. So if the curve is traced multiple times, you're going to get multiple times the arc length that you actually want. All right, so let's look at a quick example using this arc length formula. Because Infinite Campus is down, I can't get into my network drive, so I can't pull up a picture. But we're going to use our favorite cardioid. We want to find the perimeter of r equals 2 plus 2 cosine theta. This reminds me of the perimeter. Reminds me in one class that I took, I got points off on a homework problem because I said a hexagon had a circumference. And the grader said, no, only circles have circumferences, hexagons have perimeters. And they took points off on my homework assignment for that. According to that grader, only circles have perimeters. Right. I think perimeter is just, or the circumference is the perimeter around the outside of any shape. Not according to that grader. All right. And it wasn't just a little bit of points. It was several points. All right, so there is a rough sketch of our cardioid. Yeah, this one's more kidney shaped than cardioid shaped, but it's pretty close. The curve is traced once on 0 to 2 pi. If you weren't sure, you would either graph it in your calculator or solve for the theta values when r equals 0, and you would see that you'd get your two values to be 0 and 2 pi. And what I'm going to do is do the top half times 2. All right, so r prime is minus 2 sine theta. R prime squared, we need that, is 4 sine squared theta. R squared is 2 plus 2 cosine theta squared. So we get 4 plus 8 cosine theta plus 4 cosine squared theta. And this looks a little intimidating. So we're going to say r squared plus r prime squared is 4 cosine squared theta plus 8 cosine theta plus 4 sine squared theta. All right. Sine squared plus cosine squared is 1, and we have a factor of 4, so we get 8 plus 8 cosine theta, which equals 8 times 1 plus cosine theta. Oh. So our arc length is 2 times the integral from 0 to pi. What a coincidence, right? The square root of 8 times 2 cosine squared theta over 2. We just saw that on our opener. Sorry, integral of the day. So this comes out to be, we get 16, we get 8. The integral from 0 to pi. I need to be a little bit careful here. The square root of cosine squared theta over 2 is absolute value of cosine of theta over 2. We need it to be positive. Square root of something squared is always positive. We had 16. We took the square root of 16, which is 4. Multiply the 4, and we get that 8. All right, but we're okay here, right? Because on 0 to pi, is cosine theta over 2 negative? No. No. So we're good. We don't have to split it up. We don't have to worry about when it could be negative. So I'm going to say cosine theta over 2, that's what saves us, is greater than or equal to 0 on 0 to pi. So we don't have to worry about the absolute value. We can drop the absolute value. And we get that the arc length, so S equals 8 times 2 sine theta over 2 on 0 to pi. Remember that trig functions often have a positive value when theta is 0. So we get 16. So arc length would be 16 units. You could just write units or square units.
Well, this would just be units.
This would be units, yeah.
But if it's an area, it's units.
Right.
It's not provided in.
Right. Just units. And if you didn't put anything, that's fine for me. In math, you can put the units in physics class. It's just something. It's 16 somethings.
16 units.
All right. Let's look at surfaces of revolution now. We've seen this in a number of contexts. And we're going to apply the same thinking that we did in rectangular coordinates. That we're going to view this area of a surface of revolution as a frustum of a cone. So we're revolving our curve about an axis. We're going to talk about little pieces of cones, and we're going to use the exact equations that we use for parametric equations. But with the substitution, x equals r cosine theta, and y equals r sine theta. So our arc length is 2 pi. So we have the circumference of the circle. The integral from alpha to beta, and I'm going to say r of theta sine theta. That's our radius of revolution, and we're going to say the square root of r squared plus r prime squared d theta. That's our little piece of arc length that we're revolving. And what axis are we revolving this about?
X.
X, and in polar coordinates?
Axis.
About
The pi over 2.
theta equals 0, the polar axis. Well, there's no x in polar coordinates.
Yeah, come on.
Yes,
Okay.
And if we revolve about the pi over 2 axis, we get r of theta cosine theta. That's our distance from the pi over 2 axis. And then our little piece of arc length, r squared, square root of r squared, r prime squared, d theta. And this square root of r squared plus r prime squared d theta, you could view that as ds. And this is about the pi over 2 axis.
They just call it the pi over 2 axis.
Huh? The pi over 2 axis.
You're reading the Gorman
The Gorman axis. And you could also call it the pi. You could also say about theta equals pi over 2. You could say this is about theta equals 0. Pi over 2 axis sounds nice though. All right, and just like before, you want to make sure your curve is traced only once on the integral evaluation. And I'm going to give you a hint when you're doing these, when you're evaluating these integrals for finding r prime. So this can be helpful. For equations, in the form r squared equals f of theta. So maybe a lemniscate, figure 8 shape. To find dr d theta squared, So we need that in our arc length integral, drd theta squared. Use implicit differentiation.
Oh, wait, isn't that how
I'm going to move that down so I have room for the entire word on one line. So we can say 2r, if we differentiate implicitly, 2r drd theta equals f prime of theta. And then we can say drd theta is f prime of theta over 2r. And you can square that. So this is easier. Often it's easier than taking the square root and dealing with the derivative with the square root. Yes?
How do you deal with the r? You sub in from the...
Yeah, you sub in from this. So let's look at an example. So let's say we had r squared equals 4 sine theta. So for our arc length integral, for our surface area, surface of revolution, we need the drd theta squared. So for this one, I would say 2r drd theta equals 4 cosine theta. So drd theta is 4 cosine theta over 2r, and drd theta squared, which we need in our integral, is 4 cosine theta over 2r squared, which is 16 cosine squared theta over 4r squared. And we have r squared right here. So that's going to equal 16 cosine squared theta over 16 sine squared theta. Sine theta. And we could write that as cotangent theta times cosine theta. Cosine over sine, and we have one left over cosine. So that would be what you would sub into your integral. That one could be a kind of an interesting integral, depending on what else is involved there. So that can be easier than taking the square root and then dealing with your derivative with the square root. You don't have to do it this way, but I think it saves a little work. All right, questions? Okay. If you wrote down the homework that I originally had written down for Friday, on Friday, you already have it written down.